So in the last class, we understood that for a stationary process to be White's and stationary, we need two conditions to be satisfied. The first thing is that the mean should be a constant, and the second one there is that autocorrelation function should also be time invariant. Now, we do not know what is autocorrelation function. What do you think is an autocorrelation function? So listen here. Before you write notes, you can listen here. Autocorrelation means, what is meant by correlation? What do you think would be correlation? You might have studied in statistics in your schools and in your first year or so on what is meant by correlation. What do you think is correlation? Relationship between two variables. What is the correlation between your results and your marks? Sorry, your results and your attendance. More attendance, naturally more marks. If you are attentive. Relationship between two variables, whether a variable when is increasing, the other one will increase or decrease or something like that. So correlation means when one variable increases, what happens to the other? What is the relationship between them? Autocorrelation means relationship of the same variable with the same variable at a different point of time. Autocorrelation is the relationship of self with the variable with the same variable at a different point of time. This is called as autocorrelation. Okay, I told you that entire stochastic process, everything is time dependent. You have time variables. Time is a very important uh, variable or dependent variable in a stochastic process. So definition for autocorrelation. So here I put the definition in the simplest of all terms. Correlation is a matching process. Autocorrelation refers to the matching of a signal with its own delayed version. The autocorrelation function of a real valued energy signal x of t is defined as Rx of tau is equal to minus infinity to infinity x t plus tau dt, where t is between minus infinity to infinity. The autocorrelative function of a real valued signal has the following properties: symmetric about tau, Rx of tau is less than Rx of 0 for all tau. The minimum value occurs at the origin. Rx of tau, phi x of tau, autocorrelation and ESD form a Fourier transform pair as designated by the double-headed arrows. So when you wanted to convert this time domain into frequency domain, we can opt for this. Rx of 0 is equal to minus infinity to infinity x square t dt. Value at the origin is equal to the energy of the signal. These are the basic properties of autocorrelation function. We'll be seeing it in detail also. So now let us study what is the definition of autocorrelation process, or how we are going to find out the autocorrelation of any random process. The autocorrelation of the random process x of t is defined as the expectation of the product of two random variables at two different points of time t1 and t2. Rx of t1 comma t2 is equal to E of x of t1 and x of t2. That means, in other words, it is equal to minus infinity to infinity integral double integral x2 x1 x2 fx t1 x t2 x1 comma x2 dx1 and dx2. This is how you are expected to find out the autocorrelation of a random process x of t. We have seen basically in points for autocorrelation function properties. Now we'll see in detail the properties of autocorrelation function. The reason why I gave you two different slides for the same thing is that you may get a short question as well as a long question for this. So you may need to write in detail when you get a question that is for 10 marks or 7 marks. But for 3 marks, you just need to write the 4 or 5 points that is already mentioned. For the convenience of notation, we are going to define the autocorrelation function of a stationary process x of t as Rx of t is equal to expectation E of t plus tau x of t for all values of t. Okay, this autocorrelation function has several properties. First property, the mean square value of the process can be obtained from Rx of tau simply by putting tau is equal to 0. If you are asked to find the mean square value of a process, you need to find out Rx of 0, that is nothing but E of x square t. The autocorrelation function Rx of t is an even function of t. That means that Rx of t is equal to Rx of minus t. The autocorrelation function is an even function. That means the negative values will be same as the positive one. This property follows the definition in the previous equation, and accordingly we'll find that the autocorrelation function Rx of t to be equal to E of x of t minus tau. The third property of autocorrelation function Rx of t, autocorrelation function Rx of tau has its maximum magnitude at tau is equal to 0. That is Rx of tau absolute is always less than or equal to Rx of 0. And this property you may need to prove. It's very easy. To prove this property, consider the non-negative quantity E, expectation of t plus tau, plus or minus x of t square, which is always greater than or equal to 0. On expanding this, you're splitting this 2. You get it as E, expectation of x square t plus tau, plus or minus 2E x of t plus tau, x of tau plus E x square t is always greater than or equal to 0. So, from the previous equations, what we get is that 2Rx of 0 plus or minus 2Rx of tau is greater than 0. So, Rx of tau will be always between minus Rx of 0 and Rx of 0. Now, autocorrelation function of a wide sense stationary random process. Just as the variance provides a measure for randomness for random variables, the autocorrelation function provides a similar measure for the random process. For all random variables, we are calculating the variance to know how far is it deviating from its original values or from its generally accepted values. Similarly, for a wide sense stationary process, here what we will be doing is that we will be using autocorrelation function as the main function to find out how far is the stochastic process different from the original stages. Okay, so for a wide sense stationary process, the autocorrelation function is only a function of time difference tau, which is defined as t1 minus t2. That means that Rx of tau is equal to expectation E of x of tau, x of t plus tau, where tau stands between any values from minus infinity to infinity. So we are studying wide sense stationary process. We will study the properties of the autocorrelation function of a WSS process. So properties of autocorrelation of WSS, wide sense stationary process. Rx of tau is equal to Rx of minus tau, symmetrical about its origin or symmetrical about 0. Rx of tau is always less than or equal to Rx of 0 for all values of tau. Rx of tau, the Fourier transform pair Gx of f. Okay, we'll be learning what is power spectral density in the coming slides. For your understanding for the time being, I can tell you that power spectral density is nothing but the Fourier transform of autocorrelation function. Okay, Rx of 0 is equal to E x square of t, the value at origin is equal to the average power of the signal. Gx of f, in other terms, the power spectral density is nothing but the Fourier transform of the autocorrelation function. LTI systems. So let us study what is linear time invariant systems, LTI systems. Suppose there is a random process X that is applied as an input to the linear time invariant filter with the impulse response h of t producing the random process y of t at the filter output as shown in the diagram or shown in the figure. You have a random process x of t, you are giving it as an input to the impulse response system and with a transfer function that is h of t, and you are getting the output y of t. Okay. In general, it is difficult to describe the probability distribution function of the output of the random process y of t even when the probability distribution of the input random process x of t is completely specified for minus infinity, for t between minus infinity to infinity. So now what we are going to study is that we are going to study the stochastic process for linear time invariant system. So we are considering an input random process x of t, output y of t through an impulse response system of h of t. So let us consider transmitting this random process through a let us consider transmitting this random process through a linear time invariant system. So the output will be given as y of t is equal to minus infinity to infinity h of t1 x of t minus tau 1 d tau 1, where tau 1 is the integration variable. So let us find out the mean of this function, which is nothing but e y of t. That is equal to e y of t. Are substituting for y of t from this. This value is substituted here. So now let us find out the mean mu x. Mu x is defined as integral minus infinity to infinity h tau 1 e x minus t tau 1 d tau 1, that is equal to minus infinity to infinity e of x t minus tau 1 is nothing but the mean mu x. We are finding out mu y, the mean of the output random variable. Okay. So in that case, what we'll get, if it is a white sense stationary, what happens? Mu x of t will be a constant. So we will get mu y is equal to mu x minus infinity to infinity h of tau 1 d tau 1 mu x h of 0. That means that the output of a linear time invariant system mu y is equal to mu x h of 0, where h of 0 represents the zero frequency DC response of the system. So we have derived the equation for the mean of the white sense stationary process when it passes through a linear time invariant system. I hope all of you are clear with the derivation. Am I right? The mean of the random process y of t produced at the output of an LTI system in response to a random process or a stochastic one, x of t, acting as the input to the process equal to the mean of the x of t into the DC response of the system, which is intuitively satisfied. That means from the previous slide, we have proved that the mean mu y of t is equal to mu x of t into h of 0. Okay. Considering the next autocorrelation function of the output random process y of t, we have ry of t comma u is equal to e of y t y u, where t and u are two different points of time, two values of time at which the output is observed. Therefore, ry of t comma u will be equal to, from the previous we have seen that it is equal to minus integral minus infinity to infinity h of tau x of t minus tau 1. We have 2 points of time, tau1 and tau2, t and u. Like what we have done for the previous derivation, what we are going to do is that we are going to substitute the value of e of x square of t. In that case, the autocorrelation function of R, that means autocorrelation function of the output of a linear time invariant system R YTU will be defined as integral minus infinity to infinity d tau1 h t1 integral minus infinity to infinity d tau2 h tau2 e of x t minus tau1 x u minus tau2 at two different points of time, t and u. On simplification, you will get this equation. When we consider this x of t to be a stationary process, then the autocorrelation function x of t is only a function of the difference between the observation at two times, t minus tau1 and u minus tau2. Then on substitution, you will get that r y of t is equal to minus infinity to infinity double integral h tau1 h tau2 rx tau minus tau1 plus tau2 d tau1 d tau2. So from the previous results, the mean the mean of the output mu y, we see that is a stable linear invariant filter and is a stationary process. So the output of the filter will also be a stationary process. In that case, the output E y square of t is equal to minus infinity to infinity double integral h of tau1 h of tau2 rx of tau2 minus tau1 d tau1 d tau2. This is also a constant. So what is the significance of these two derivations? In this particular derivation, we have understood that the characteristics of a wide sense stationary process when it passes through a linear time invariant system. You understood? All of you. What is a wide sense stationary process? A process which has two important characteristics, that is its mean is constant and the autocorrelation function is a autocorrelation function is time invariant. That means that Rx of t plus or minus tau is equal to Rx of tau. Am I right? Yes or no? So what happens in this when we substitute the values and we find out the mean and the expected values mu y, we get that to be a constant. So when a wide sense stationary process passes through a linear time invariant system, it remains to be a wide sense stationary process. That is the significance of these two derivations. Now all of you understood? Next, power spectral density.